If we have a stand with a rotary device here, and that's attached to a string, attached to a pulley, and a mass hanging down like that. So this is basically the moment of Inertia Lab. We have some from this is a side view. This is some mass m here, and then we have a mass of this object that's turning here, moment of inertia I. From an overhead view, we have a pulley, axis of rotation right here, and then we have a mass sitting here which is going to go in that direction. Initial velocity is 0. If we did a force diagram of the mass here, we have weight acting down and we have the tension acting up. And then if we did a force diagram here, we have some tension pulling on it this way. And then we're going to have some friction acting back here. And so if I do the force diagram here, I've got a torque involved here. So here I'm plugging in a torque equals I alpha. And here I'm plugging in into F equals ma. Center of mass is not accelerating here. We could go through there, and actually if we wanted to find out some sort of coefficient of friction, I'm sure we could, but not necessary. So we have two torques involved here. Let's do the easy one first. So this one is going to accelerate downwards, and this is going to accelerate, it's going to accelerate around like that, which says that the acceleration actually is down into the page. So my angular acceleration is into the page because it's rotating clockwise, and clockwise, if you recall, your fingers curl around in the clockwise direction, thumb points in the direction of the vector. So I am going to set up a coordinate system so that down is positive, into the paper is positive, and so if that's my j direction and that's my k direction, then in a right-handed coordinate system, I know that j cross k equals I. So j cross k, let's make sure I'm doing that right. J cross k, put I in that direction. And we can just confirm I cross j is equal to k, I cross j equals k, and that works. So I'm going to have a j equation here, that w minus ft is equal to mass times acceleration. Here I'm going to have a torque equation. This will be my k equation right here. The fact that the tension times the moment arm minus the torque from friction is equal to I alpha. I guess I don't need the vector symbol there since we've already identified in the k direction. So those are my two equations that I'm working with to start. And so on to actually combining the two. So I have W minus tension is equal to MA. This was my J equation. I know that's mg minus the tension is equal to MA. And so therefore the tension is equal to mg minus MA, just flipping sides here. And flipping the sides of those two terms and then flipping the overall equation. And so that's equal to mass times g minus a. So the tension is the difference between the weight and the mass times acceleration. Now we have for our k equation, we have the tension times the moment arm. So this r is the radius of the disk, and in the lab that we did the long one. We found the diameter, so the radius is just going to be half that value. Minus the torque from friction is equal to I times alpha. Now, the torque from friction, if we had a situation where we were only measuring the acceleration, angular acceleration, with friction as the only force acting on it in that particular direction, then we could actually find that, and we did. we separately did a torque from friction, and that's equal to the moment of inertia, which has already been calculated, times alpha. So I'm going to call that alpha 1 here. So that for the lab was part D and E. And I'm going to call this alpha 2. So this is from procedure D or E, depending upon if it was just the aluminum disc or the aluminum disc and the steel disc. And this is the part from F or G, depending upon if it was just the aluminum disc or the aluminum and steel disc. So therefore, that's going to fit into there. So the tension times that moment arm is equal to I times alpha 1 is equal to I times alpha 2. Bringing that term over and then substituting that in for tension, I get M times G minus A R equals I alpha 1 plus I alpha 2. And that's I alpha 1 plus alpha 2. And so the moment of inertia is going to be M G minus A times R over alpha 1 plus alpha 2. From experimental results, in parts procedures F and G, we found A, we found alpha 2. Alpha 1 we found from a previous part, mass we have measured, and R we measured. And so we can calculate experimentally the value of the moment of inertia I, and then compare that to the Vernier relationships. And so that's how you do the analysis for, or find the moment of inertia for parts F and G. For part H, if you recall, the graph looked something like this. It was almost continuous there, but there was a kink. That's where there was definitely a kink in the graph. And I want to figure out what is the velocity at this point right here. I need to know final and afterwards, because I'm checking if angular momentum initial equals angular momentum final. So in this context right here, if that's where the interaction happens, is that where the collision, or where I drop one on the other, this point right here is the initial, this point right here is final. So for this context, so just before and just after. Now we identified this time as that halfway. It was 7.12 seconds. I'm going off memory on that one. Do it based upon what's in the video. Just for the sake of this, I'm going to say 5 seconds. I mapped out, I did a curve fit for a section beforehand. I did a curve fit for a section afterwards. So what the equation was, I did a quadratic fit, so you'd end up with theta is equal to, I'm just picking numbers at random. These aren't the actual numbers, so let's say negative 1.5 radians per second squared t minus 4 radians per second, no, that should be t squared, minus 4 radians per second t plus 7 radians. And here would be something different, so theta is equal to, again, making up numbers, negative 0.5 radians per second squared t squared minus 3 radians per second plus 1. Now, these equations here are classic cake formulas. These are the angular cake formulas, or in one source I wrote it as C-A-A-K-E. We know that delta theta is equal to omega I t plus 1/2 alpha t squared. So this is theta final minus theta initial is equal to omega I t plus 1/2 alpha t squared. If I bring theta initial over to the other side, I have theta final equals, and I'm just going to change the order around. I'm going to do that first, 1/2 alpha t squared plus omega I t plus theta initial. So this is the format that we're looking at right here. So if we're looking at that equation, that is negative 1.5 t squared minus 4t plus 7. Look at the map ups here. Omega initial is negative 4, theta initial is 7. We don't really care about that. And 1/2 alpha is equal to negative 1.5. So therefore alpha is equal to negative 3 radians per second. Omega initial in this formula is negative 4 radians per second. Now it is heading in that particular direction, so I can then project at this particular point what the velocity was based upon before the collision. So I plug 5 seconds in for time. Well, I'm trying to find omega here, because back to here, angular momentum is equal to I times angular velocity. And that'd be I times, this is initial, final omega. Before the collision, this I here, this is I of the aluminum times omega initial equals I of the aluminum plus I of the steel times omega final. So I'm trying to find this omega I, that is the omega just before the collision, which is actually not the same as this one right here. This omega here is the omega at the beginning of the, well, basically it maps it back onto the axis. This omega I here is the omega at the beginning of this mapping right here. It's not the omega at this point right here. So what I need to do is find the angular velocity at this point right here. So I'm using omega final. I'm going to call it 2, omega 2. So this is at point 2 right here. Omega 2 equals omega I plus alpha t. This omega initial, negative 4 plus negative 3t, and I'm plug in, I just made up 5 seconds there. So negative 4 minus 3 times 5, which is negative 19 radians per second. That is the angular velocity just before the collision. Just after the collision, I'm mapping this right here. I'm going to go through the same process. I'm going to take my quadratic equation, parse from it my alpha and my omega, and then use that equation with these new alpha and omega. At 5 seconds, I can find the velocity just after the collision. And now I'll have those two values right there. So this is, I guess, omega 2 initial and omega 2 final. And so lastly, I asked you to find the ratio. So IA times omega 2 initial equals IA omega 2 final plus IA plus I steel, which I'm just going to label as F for right now, omega 2 final. Get these together, so I have IA omega 2 initial minus omega 2 final equals I of the steel omega 2 final. And then the ratio I asked for was either IA over IF or IF over IA. I asked for IA over I of the iron, IAL, over I of the iron of the steel. And so bringing this on this side, bringing that on that side, we get omega 2 final over omega 2 initial minus omega 2 final. That's the ratio that we're looking for there.